Yeah, comes on everyone. Let's start off. There, today we will start off with wave optics and ray optics. So initially we will start with wave optics today. That's a more important one. Ray optics is also important, but still formula based. Now at a mains level, wave optics is quite easy actually because they really don't ask too much of the twisting and all. They don't do that. But advanced level, it's really deadly. Right? So advanced level, right? If you see, there are few topics like which you should definitely do. One is like rotation, that is anywhere there. Then we have AC circuits, right? EMI, modern physics, wave optics. So these are like the main things, which they can ask questions from different things. So advanced perspective, these are really important ones. At a mains level, it is fine. So let's see a few questions on this, and then we'll go ahead. So here we got a thing there. This is the source. Observer is here. This is the light source. This is a question from the class notes though. 90 and this is T. And the wavelength is lambda. Find lambda if he sees a destruct interference. Same thing, repeated for a sound wave. This is a standard question, like easy one, but you should know what is the difference between them. What is the catch? When a light ray hits a mirror, what will happen? You get an extra path difference, lambda by 2. But when a sound ray reflects, nothing happens. That is the only difference there. So here we are getting one light ray comes directly to the guy, and one light ray will hit and bounce and come. And because a light ray reflects, this will create an extra phase difference lambda by 2. So let's call this point A. Let's call this guy SP. So path difference would be S2A plus lambda by 2 because of reflection plus A2P minus SP. So this will be 2D plus lambda by 2 minus D root 2. Since he's seeing minima, then this will be 2n plus 1 lambda by 2. So be careful. Whenever a light ray hits a mirror, it will always get an extra lambda by 2. But whereas in this case, the sound comes directly here. This will be SA plus AP minus SP. Clear with this? Easy one, but understand the difference between that, the mirror and a sound wave. S1, S2, S3. Everyone knows how to do with the YDAC with, two sources. But what happens if there are three sources? Again, this would be beyond mains, but it's a good one. This will cover a lot. Let's say we have three sources. This phase angle, let's say this intensity is I, this intensity is 2I, and this intensity, let's say, is 4I. Let's make it same only, maybe I, and let's say this is 4I. S2P minus S1P is lambda by 6. S3P minus S1P is lambda by 3. Find the intensity at point P. How do we do this thing? It's a good one. See. So this will give you a phase difference phi, 2 pi by lambda, lambda by 6. If your cams are not on, I'm going to remove you from the classroom. So that is the reason some of you got kicked out, in case you didn't realize. So do keep your cams on. So 2 pi by lambda by 6, and that would be pi by 3. This guy will give you a phase difference of 2 pi by 3. And we also know I is proportional to amplitude square. That means if you look at the first source, y1, the amplitude is a sine omega kx minus omega t. For the second source, the amplitude is also a because the intensity is same, but you have a phase angle of pi by 3. For the third one, the intensity is 4i, that means the amplitude is double, and the phase angle is 120 degrees. Hope you're getting it. So these are the three waves which are going and meeting there. And how do you add three waves? Remember phasors? So if you have three waves with a phase angle phi, then we use phasor. So the first one, sine omega t minus phi, that means the phase angle is 0. So you treat the amplitude as a vector and the phase angle as the angle with the horizontal. A. Second vector is making amplitude A and the angle 60 degrees. This thing, the first time we discussed this thing was in SSM. The third thing is making two-way with an angle 120 degrees. Clear with this? So if you add these three vectors, we get the resultant amplitude. So this guy will be A. This will be also 60 here. This will be 2A cos 60. This will be A. This will be A sine 60 plus 2A sine 60. The horizontal will cancel out, and that will be 3A sine 60. That will be 3A sine 60 is root 3 by 2. That's your amplitude at point P. And since I is proportional to A square, IP will be, how much is that? Square that. Three root 3, that is 9 into 3, 27 by 2y. Is that clear, everyone? 13.5. Sure with this? That means the amplitude of the net resultant when it reaches will become 3a root 3 by 2, and uska square will be 9 into 3, 27 by 4. Clear with this? Close to 7a, but it's not 7a. There, it's a good one. If you remember in the class notes, we did I, 4i, and 9i. We also get a cos 60. This cos 60 and 2 will cancel with a, na? Horizontal is getting cancelled, right? नहीं?
सर वो a प्लस a cos 60 है ना, और वो 2a cos 60 है.
हाँ सही है. There is one more a cos 60. Yeah, I forgot. Then what will be the resultant then? Square them and add them. That will be root over 28 by 4 a root 7. Yeah, you are right. 7a. There is an a cos 60 also. There, it's a good question. So this is what you do when you have more than two sources, because everyone knows how to handle two sources. The moment I get a third source, people get confused like how to handle that. So it's a good one. Check it out. In class notes, we did I, 4i, and 9i. So S1, S2. So you're sending a parallel beam of light. Let's say this D is 3 mm. This is x is equal to 0, and let's say this D is equal to 3 meters. There is a point P here. This is x. Find intensity at point P, first case, when x is equal to, let's say, 3 mm, 4 mm. B case, when x is equal to 4 meters. The intensity is I for each of them. The first question is proper mains level equation. Second thing becomes an advanced one. Let's give it a try. Yeah. फर्स्ट तो ऑफलाइन ही है, पेन पेपर है. ऑफलाइन के लिए तो उसमें है ना 11th and 12th ईयर के लिखा था ना, फर्स्ट दो फाइल चेंज रहते नहीं करे. हाँ, वो ऑफलाइन के लिए भाई यूज करेंगे. ये सही है. और बाकी टीचर सब लोग देख लिए ना. हाँ बोल रहा था थोड़े पेपर बेस्ड दीजिए बाद में. तो क्या करें. चलो. You guys didn't forget how to do this stuff. See, listen, I'll give you some basics. In entire wave optics, now the whole story is about finding the path difference. If you know how to find the path difference, your job's done. So listen to this. So this is S1, this is S2. So they're going and hitting somewhere here at point P. This distance is D. Since it is very, very far, you can actually directly drop a perpendicular here, and you can argue this will be the extra path difference it will travel. So it's like we are saying this path and this path are equal. So this would be your extra path difference. Okay. And if you take this angle to be theta, that will be 90 minus theta. This is theta. So we get the extra path difference delta x is equal to d sine theta. There we get it in one step. You can do this also. If you remember in the class, I taught you even something like this from the center. That is actually good because if you remember when we are taking circle or something, then this will be difficult. This also works because end of the day you're approximating, you can do any kind of approximation. So that you can do this much faster. Path difference d sine theta. This is actual path difference when you take from x from here. Okay. So the path difference should be technically delta x is d sine theta. Now, if x is small, if that x is much, much smaller than d, then theta also will be small. Then we did an approximation. Sine theta becomes approximately equal to tan theta, and tan theta becomes x equal to d. So we get delta x is equal to dx by d. At a mains level, this is the thing which you should definitely remember. So at a mains level, they're not going to mess up with the YDAC. They will keep the YDAC the standard experiment only. In a standard YDAC experiment, x is always small. So theta is small, right? So this is the formula used when x is small. This is the formula we have to use when x is large. So sine theta will be x by root over d square plus x square. Once you got the path difference, you get the phase angle, which is 2 pi by lambda delta x. So which formula you use for path difference depends on what is the value of x. Once you got the phase angle, the intensity will be I1 plus I2. If the intensities are not equal, then the formula is I1 I2 2 root I1 I2 cos phi. There. These are literally everything in YDAC, isn't it? They can ask you intensity, they can ask you the path difference and all this stuff. Now coming back to our question. So in the first part, you said x is equal to 4 mm. So use your regular formula, delta x is equal to dx by capital D. In the second case, he said x is equal to 4 meters. Then use that formula d sine theta, which is dx by root over x square plus d square. From here, you get the phase difference. The story will be same from here. 2 pi by lambda delta x. Since both the intensities are same, then I resultant will be 4i cos square phi by 2. If the intensities are different, then use that formula I1 I2 plus 2 root I1 I2 cos phi. Clear with this? That is a deal about that 4 meters and 4 mm. Generally, at the mains level, they'll just stick to the 4 mm thing. Clear with this? Especially, you should definitely check out the notes. We wrote something like around 10 cases. Yeah? What happens if I use white light, if I use particles, if I replace with bulbs? So there are multiple things. You should definitely check out all those stuff. And this is another important thing. Remember, when you put a slab in front of it, what happens? Again, for people who don't remember, what happens if you keep a slab in front of it? Let me explain you that also. See. So when you put a slab in front of it, remember, whenever you have a glass slab of mu, this behaves as if this is equal to a vacuum, or let's say if it is surrounded by a medium m, this behaves like a medium mu m, whose thickness will be mu by mu m into t. That is an equivalent length. Getting it? So if you replace the slab mu with a medium mu m, it feels as if the length has become mu t by mu m. So when a light ray passes through this, the time must be same. That was the concept there. So if a light ray passes through the slab, it will travel t. But if it passes through, the medium, it will travel more. So the extra path difference because of the slab, the light will think it has traveled extra distance, which is t into mu slab by mu medium minus 1. Remember this formula. Clear with this? This is valid for thin slabs. So now when you go and put a thin slab in front of it, T1, mu1, you should check out the notes in case you want more detailed derivation there. T2 and mu2. Story is the same. You want to still find the path difference. So one light ray is going like this and light ray is going like this. So what is the path difference for delta x? Light ray is going from S to P, but while going through S to P, you pass through a slab. So there is an extra distance, T2. And let's say this whole region is surrounded with medium also. If it is vacuum, you will take 1 anyway, mu slab, that is mu2 by mu medium minus 1. So the light ray going from S2 to P will think it traveled an extra distance this much. Minus the light ray which is traveling through S1 will think it has traveled T1 mu1 by mu medium minus 1. This is the new path difference. But what is S2P minus S1P? That's your regular standard value, which is dx by capital D. This much, if you remember, you can derive everything in this actually. Most people try to mug up that final result and it goes over the head. This is the path difference at point P because if you keep slabs. Now what they will ask you, find the position of central maxima. What is central maxima? Central maxima is a position where delta x is 0. So if you put delta x 0, you will get the position of central maxima. The fringe width will not change. Fringe width is independent of whether you put the slab or don't put the slab. So once you got this delta x, so sometimes you'll hear questions like this. When a slab is placed in front of the slit, it is observed the fifth maxima has come to the position of central maxima. Meaning central maxima shifted by 5 fringe widths. So indirectly he is giving you the x value. So central maxima delta x is equal to 0. So x will be d by small d. Now people try to remember this one. Huh? This is unnecessarily messed up. I would suggest you remember this one. That is easy to derive. Confusion bhi nahi hoga. And what if I keep only one slab? Right? So you will be able to play around. What if I keep 2 slabs in front of back to back? So it will not be difficult. Then you'll understand where to change. But if you just try to remember the final result, then you will not understand what the hell is happening if I change something. Mu2 by mu medium minus 1. What is this? This is the shift of central maxima. So whenever you keep a slab in front of it, the whole pattern will shift. Clear with this? Fringe width will not change. Clear? And they can ask you multiple questions like, if the central maxima does not shift, find the relation between them. So x must be 0. Clear? The shift of central maxima. So this is some pretty good questions when you put slabs. So I think now can you do this? If you remember in wave optics, again, just to brief it, in wave optics, the primary thing is to find the path difference. If you know how to find the path difference, 80% of the chapter is done. Okay? Now, how can you get path differences? There are 3 ways. 1, make them travel different distances. Second, make them reflect on a mirror. You get extra lambda by 2. Third, make them go through a slab. These are the 3 ways you can create a path difference. Clear with this? That's it. As long as you understand this and you know these 3 cases, you can handle most of the problems. Even at an advanced level, you'll be able to handle. Let's get this. In an Young's double slit experiment, light of wavelength lambda, intensity of the central fringe is I0. Now, one of the slit is covered by a glass plate of refractive index 1.4, thickness 5 micrometer. The new intensity at the same point on the screen will be. Central fringe basically is asking intensity x is equal to 0 only. So yeah. Try, you got a minute. Let's see. Yeah, is the answer. You guys got it. So we got a slit here. You took a slab and kept it in front of the slit. So you're talking about this point ka path difference. Initially, the path difference used to be 0. So after keeping the slab, the new path difference will be because of the slab only, which is T into mu slab by mu medium minus 1. They didn't talk anything about the medium, so we'll take it as vacuum. So T will be 5 micrometer, that is 5 into 10 power minus 6, and the mu slab is 1.4 minus 1.4. So the phase angle will be 2 pi by lambda, which is 600 nanometers, which is 10 power minus 9. That is 2 into 10 power minus 6. This will be 2 pi by 3, 20 pi by 3. Hmm, 10 power minus 3 to 20 pi by 3. 20 pi by 3, you can remove 2 pi's from this. This would be how much? 6 pi plus 2 pi by 3, no? So 2 pi is anyway 0, so this phase angle is 2 pi by 3. So now the new intensity IR will be I naught, that used to be the initial intensity, 4 cos square 5 by 2. That will be I naught, cos square 5 by 2 will be cos square 60, that will be I naught by 4. Clear with this? Clear how they're playing around? So end of the day, it is always about the phase. Once you got delta x, you'll get everything after that. Clear? So if you remember the formula, this is what will happen. You will get confused which formula to use and also keep it simple. Let's see one more. Hope you guys remember this. Refraction on a thin film, interference on a thin film. this is yeah. A glass plate of refractance 1.5 is coated with a thin layer of thickness T and refractive index 1.8. Light of wavelength lambda traveling in air is incident normally on the layer. It is partially reflected at the upper and the lower surface of the layer, and the two reflected rays interfere. Write the condition for constructive interference. This itself was a whole experiment, actually, if you remember the interference on thin film. In case you forgot, let me explain you the theory. So this was the glass slab. This is a thin film. So the light rays are incident almost normal. So one light ray will come and bounce off like this, right? The other light ray will go inside and then will come off. So I'll do one thing. For convenience, I'll change the color for them. So the other light ray is hitting the inside and coming off like this. So this red one, now you are going from air, mu is equal to 1 to mu is equal to 1.5. So you have to be careful here. And glass slab is 1.8. And glass slab is 1.5. Just now I told you, whenever there's a reflection, there will be a phase difference of pi, but there's a catch. It should be always from rarer to denser. Whenever there's a reflection from rarer to denser, if you remember in waves, when a wave goes from a light string to a heavy string, rarer to denser, then the reflected wave will be inverted. There will be always a reflected wave. So you will get a phase shift of pi. But if you go from denser to rarer, it won't happen. Remember this? So just because there's a reflection, don't put phi every time. You have to be careful whether it is going from rarer to denser or denser to rarer. So for the red one, you're going from air to a glass slab. So it's going from rarer to denser. So this guy will have an extra part difference of lambda by 2. The green one, it is going from 1.8 to 1.5, that is denser to rarer. So there'll be no phase shift. But you're traveling inside a glass slab, so you will have an extra part difference to mu t. Isn't it? When you travel through a medium, it feels you have traveled more distance. So the path difference delta x will be, the green one is traveling 2 mu t, this guy is traveling lambda by 2. You want to see constructive interference and lambda. So from here you'll get t ka value. Clear? Easy to solve. You should know what you're doing. It will not take much time though. Clear with this? Suppose if the thickness of the film was 1.5 and the glass slab is 1.8, then even the green one will have an extra lambda by 2. You're getting it? So you have to be careful what is the mu. So don't blindly put the results every time. You have to check whether are you going from denser to rarer or rarer to denser. Clear with this? I hope you guys remember this thing, wavefronts. What is a wavefront? It is all the points which are in phase. When a light wave is traveling, right, the wave travels in waves, and all the points which are in phase is called a wavefront. The light always travels perpendicular to the wavefronts. So the question is this: you are sending think the question got cut, I guess. The wavefront from mirror R and S is there. Question got cut actually. Hmm. Mhm. So AB is the wave sent and PQ is the wave coming back. Yeah. So which mirror is concave and which mirror is convex? So here AB is incident. PQ is reflected. I told you whenever you give questions like this, convert the wavefronts into light rays. Then it will be easy to see. So how do we do this? Look at the first one. AB ka wavefront, right, is coming like this. Meaning the light rays are going, object is here, light rays are going like this. After this, the wavefront, see how it is looking. The wavefront is like this. So if you see, the wavefront was same actually. Whatever went, it came back the same way. So this will happen when, if this was a plane mirror, the light rays will hit here and they will bounce back here, just like an image, no? So then the wavefront also will be like this, isn't it? Look at this, the incident and the reflected, they just got inverted. Matlab, they're just traveling backward. This happens for a plane mirror. Look at the next one. You sent a diverging thing, but it became plane. Means you sent light rays like this. After reflection, they became like this. Which kind of mirror that must be? That must be a concave mirror, and this point must have been focus, isn't it? Is that making sense? So don't look in terms of wavefront, convert that into this thing. So C option, no? Plane mirror and a concave mirror, and the object must be at the focus. So there you can get more information there. Sure with this? So that's one thing about wavefronts. This is another good one. Hope you guys remember. Number of maximas, number of minimas. Can't R be convex as well? Option hai, but then S will be concave, na? That is only option left. So if you argue like that, so yeah, it could have been concave also. There is a possibility. Because if you take a concave, object is there, light rays will still go back here. Yeah, both are acceptable. So these are the wavefronts and this is the wavefront. So this can be, R can be actually convex or plane. Both are acceptable, but the problem S will decide the answer. What about this guy? Right there, yeah. Right home. Another 30, 40 seconds. See. So how to do this question? If you choose this point here, this light ray and this light ray, they're traveling parallel, then the path difference will be so here the path difference delta x is d. If you travel parallelly, then at infinity the path difference will tend to 0. Okay. I think now from here we have to check. So for the first option, if you take 7 lambda by 2, then this will be 3.5. So for the first option, this will be 3.5 lambda, meaning there'll be somewhere 3 here, there'll be 2 here, there'll be 1 here, there'll be 1, 2, 3 here. O is minima. Yeah, that was easy anyway. Okay. So for 4.3 lambda, so if this was 4.3 lambda, that means there is 4 here, 3, 2, 1, 1, 2, 3, 4. And middle mein, this will be 3.5, 2.5, 1.5, 0.5. Yeah, there are 8 minimas. Remember that? How to count? So I'll show you one for this thing. So if you take 4.3 lambda, that means on the screen, this is 4.3 lambda. So we are sure somewhere here there is a 4 lambda. We are sure somewhere there's a 3 lambda, there is a 2 lambda, there is a 1 lambda. 0 we won't count because it's at infinity. Similarly, 4 lambda, 3 lambda, 2 lambda, and 1 lambda. There are 8 maximas. You want minimas, they will be in the middle. So 3.5, 2.5, 1.5, and 0.5. Same thing here, 3.5, 2.5, 1.5, 4.5, so 8 minima. Clear how to count this? Should definitely check out the notes. We did almost 5 different models on this. If d is equal to 7 lambda minima, that is also right. D is equal to lambda. Yeah, there's only one maxima on the screen because if d is equal to lambda, this is 1 lambda, this is 0, 0. So you're gone. There's only 1 lambda. All are right. Clear with this? So that's an important one. So you can play around like that. Let's get 2 questions. Let's see, when light is incident on the glass plate of thickness 5000 angstroms and refractance is 1.5, the wavelengths in the visible region that are strongly reflected. The word strongly implies you got a constructor interference. That is the meaning of it. So this is that slab thing only. So if you take a slab, so one light ray is bouncing off the surface. So this guy will have a lambda by 2 part difference. The other guy is going through inside here. This will have a path difference 2 mu d. So path difference will be 2 mu d minus lambda by t. This must be n lambda strongly reflecting. So lambda will be 2 mu d by n plus half. Mu is 1.5. That's 3 by 2, 3. Thickness is 5000 angstroms by n plus half. So this lambda ka value, which is 15,000 angstroms by n plus half, should lie between 7,000 to 4,000. Actually, you can guess, na? You can put numbers and check. So he's asking the wavelength in the visible region that will be strongly reflected. So all numbers between this region will work. So if I put n is equal to 0, that will be 30,000, it won't work. Then so on. So 0, 0, 0, 0, 0. We can make our life easy. That will be 4 less than equal to 15 by n plus half. 7. So put n is equal to 2. That will be 5 by 2. 360. Yeah, n is equal to 2 is working. You can check. So what are we going to get from here? So we can check each inequality now. So nf plus must be greater than equal to 15 by 7. Then must be greater than equal to actually I can go through options also, it will work. What are you guys getting? Only B, one answer only. A, B, C, D. A and B, it seems. Check it out, see if you got this. I think when I took n is equal to 2, so I'm getting it. If I took n is equal to 2, that will be 5 by 2. 2 goes up, that is 6,000 angstroms. वो तो आ ही रहा है. So 4290, you can check it out. Then in the double slit experiment, this is a very good standard question if you remember. Missing wavelengths karke we did this in the notes. So what is the second one trying to tell you? We have two slits. So exactly in front of the slits, there are wavelengths missing. That means it is forming a minima. So there is nothing big deal about this. Indirectly, he gave you this distance x is equal to d by 2. The path difference delta is equal to dx by capital D. That will be nothing but d square by 2d. Since wavelengths are missing, it must be 2n plus 1 lambda by 2. From there you get your lambda. That you can count all those things. Those will be the wavelengths which are missing. Okay. That's a good standard question. Missing wavelengths. Clear with this. So d square by 2, na? So there, d square by capital D. I think capital D is B here. There. Let's see if you remember this one. Do you guys remember this one? This is the last question in wave optics. Just to give you context, what is happening here, the light rays which hit here, they will bounce here. The other light ray will enter inside and then it comes out. So here the path difference is this distance. So we take this distance as x. Then this will be the extra path difference, x tan theta. You guys remember this? याद आया कुछ? Don't remember. This was a question. The interference on a thin wedge at an angle theta. It's fine if you forgot. That I can understand. But now, since you forgot, now you know you forgot, right? Go and revise. Forgetting is not a problem, so don't beat yourself about that. There are, I know, too many things to remember. Chemistry bhi hai, wo bhi hai. The problem is after this, what you do. So now when you take this picture here, that is x tan theta, x tan theta. But again, look at this. The light ray is going from where to where? Here, this reflection, you're going from glass to air, so denser to rarer, there's no problem. But here, you're going from air to glass, na? There is one more lambda by 2 there. So let me draw that thing, a bigger thing. The theta is very small actually. So it comes here, it bounces off. We can almost assume, they're like straight lines only. Theta is very small. So this thing will have a phase difference. Delta x will be 0. But for this guy, this and this will be x tan theta, x tan theta. And because of reflection, we are going, this is from rarer to denser. You get extra lambda by 2. That means the total path difference will be 2x tan theta plus lambda by 2. Since you want to see maximas, this must be n lambda. Then we get, for small angles, tan theta becomes theta. This will be n minus half into lambda by 2 theta. That is the distance x, right? So if you want the fringe width, that will be the distance between two fringes. So take n1 and n2. That would be, you can just remove that. So that will be lambda by 4 theta. Clear with this? No. Now, if you read the question, he's saying an observer looks down on two glass plates, one on top, the other there. The small angle created is increasing. This theta is increasing. Then which of the following is true? The entire plate surface alternates between dark and bright fringe. True. We actually get that interference pattern there. The width of the alternating bright and dark fringe aligned parallel to the line of contact increases with time. Here theta is increasing. The width will decrease actually. So B is wrong. The width of the alternating fringe perpendicular to the line of constant. The C width of the decreases with time. That is right. Aligned perpendicular line of contact of constant in time, but becomes blur. No, it'll just keep increasing. Line of contact is a bright fringe. No, this thing dark bright is there. So the line of contact is not a bright fringe. I think he's talking about this guy, I guess. That's not a bright fringe. You have an extra lambda by 2, no? That will be a dark fringe actually. Line of contact is this point. So there delta x will be lambda by 2 because this term will become 0, no? 2x tan theta. X is not there, x is 0, right? There x is 0. So we get delta x is lambda by 2. It's actually a dark fringe. There. They are good questions. Matlab they can ask you, this would be still an advanced question though, but will be. Clear with this? Then in case you don't remember this, this is how you do for this. You can do this approximation because the theta is very small. Theta is big, you can't do this. Anyone remember this Fresnel biprism experiment? Don't forget this. If you are from HSC board, 12th standard HSC board, 4 marks का derivation है. Fresnel biprism experiment. You are remembering how much you forgot? How to do this? Listen to the experiment. I know you forgot. So this is the screen there. Now, if you ask me the result, even I don't remember the result. I know the derivation, and I know I can do it in less than a minute. So here, first thing, for thin prisms, the deviation will be A into mu minus 1. That is a deviation for thin prisms. So when you take the source here, we take the light ray here, and it goes off like this. This is angle A. This is your deviation delta. So exactly from the midpoint here, we extend the line. And this is the assumption. So we'll assume as if the light rays are coming from a point S1 exactly on top of the source. That was the assumption. So when you extend this final light ray backward, that is delta. So this angle will be delta by 2. This angle will be delta by 2. That should be the midpoint. I didn't draw properly. Let's say this distance is A. Again, it's a thin prism. You can actually ignore the thickness. Then this distance will be A tan delta by 2. This distance also will be A tan delta by 2. Similarly, I can do the same thing for a light ray which is going down. This also will be 2A tan delta by 2. So the whole scenario becomes like as if there are two slits now, S1 and S2. The distance between them is 4A tan delta by 2. Since the delta is very small, you can approximate it to 2A delta. This is your small d. Now here the screen is there, and this distance will become A plus B, where B is this distance. Now they'll ask you for the fringe width. So S1, S2 will act like two sources. The fringe width will be lambda. So this guy was capital D. Lambda capital D by small d. The lambda, that will be A plus B, by small d will be 2A delta. But delta is A into mu minus 1. Substitute. Clear with the derivation. This is your Fresnel biprism experiment. You should know this. Right? I did write it more neatly here, but check it out. There. Clear this stuff, so know this thing. Now coming back to the question. Now look at the formula we got here. Lambda A plus B by 2A delta. So A and B are the distances basically. So this distance was A and this distance was B. So he's asking what will happen to the fringe width. Now if you don't know the formula, you can't solve this thing. The whole thing will look like something else. Lambda A plus B by 2A delta. Deviation won't change anyway. So the fringe width, when will it increase? If the biprism is moved towards the slit, that means you're decreasing A ka value. Anyway, A plus B is constant. A plus B is constant. So if you decrease A, fringe width will increase. True. Screen is moved away from the biprism. So if you go away from the biprism, B will increase. That is also true. The biprism having smaller angle alpha. If you have smaller angle alpha, delta will be A into mu minus 1. So A will decrease. So yeah, that is also right. Then the slit width is reduced. Slit width, where is the slit here? There's nothing like a slit width, right? That is basically, I think he's trying to say there's a bigger light source. It won't matter. Clear with this? The fringe width, if you see, is independent of intensity. Slit width will change what? Slit width will affect your intensity, isn't it? If you change the width of a slit, intensity changes. Fringe width will not, the size will never get affected. Are you clear with this? So one denominator to, I got A plus B is constant, right? You're not changing the source in this thing, na? Clear, na, Yashil? Take a break. Come back by 9:40. We'll continue from here. Do check out the derivation though. Hmm. Get this. This is something I already discussed. Let's get this. Hmm. Consider the double slit experiment. Let delta x represent the path. Mark the correct statements. This is a good one, right? Even at a mains level, na, these theoretical questions, even though these are more than one choice questions, each statement can be a good mains level question. So when can you use an approximation d sine theta? When the distance between the slits is very small compared to this thing, na? The first was right. When is the path difference valid? When this distance y is much, much greater. That is also right. When will you get the fringes equally spaced? Only when you're very close to the fringe. That is also right. If d is equal to 3 lambda, how many fringes will come? If d is equal to 3 lambda, then this delta x is equal to 3 lambda. This is 0. Infinity mein delta x will tend to 3 lambda. Means there is a 2 lambda here, 1 lambda here, 2 lambda, 1 lambda. That is also right. All right. Clear with this? I'm very interested on the first, 3 approximations. So it's a pretty good one actually. The 3 approximations are important. Clear? Let's see. This is another good theoretical one. Let's see. And this thing is, you have to think actually. Binoculars and microscopes are frequently made with a coated optics by adding a thin layer of transparent material to the lens. So the air is there. So basically think of your eye, the glass which you're wearing, there's a thin coating on top of it. वो होता है ना, when you go to the glass shop, they say na, anti-glare coating and all that stuff. Right? So something of that sort. So what do you want to do? Constructive interference between 1 and 2, that I'm not sure. Destructive interference between 3 and 4. Now, let's be very clear. Where will you stand? Your eye is here, na? Clear? Your eye is behind the lens. Light ray is coming from that side. So you tell me one thing. You want to see the image clearly, you don't want to see the image through the binoculars. We want to see the image clearly. So light ray should have constructive or destructive interference. Constructive, as simple as that, right? It has to be constructive since you want to see the image. If this is constructive, remember I told you this. If the person from one side thinks it is constructive, the other guy will think it is destructive, conservation of energy. The total energy has to be constant. You can't have constructive on both the sides. Yeah, now let's see. Constructive interference between 1 and 2, that is gone. This is gone. C is right. The speed of the light in the coating is less than that in the lens. What the hell is this? This thing took me time to figure out. What is D? C तो ठीक है. Speed of light is less, meaning what? The refractive index is more. So the problem was this. See, the coating which is there, and this was the lens. If mu of coating is greater than mu of lens, there is a possibility of getting a TIR. Isn't it? There is a possibility of getting a TIR. That means when you're standing here, if you try to look through the corner of the eye, you can't see that image because those light rays will get TIR. You're getting it? So light rays which are coming from the side, they will just bounce off or they will have a TIR. There is a possibility of a TIR. The light rays will actually go away from your eye. You want them to converge. So you don't want TIR, meaning the coating should be rarer compared to the lens. But the speed of light must be more. Are you clear with this? So D is not the answer. So you should always coat that thing with a lesser refractive index compared to the lens. Clear with this? So that's basically the anti-glare coating which people, sell. Point of anti-glare. No, this is not exactly anti-glare. Right? This is something else. Binoculars and this is a translucent material. I'm just giving an example of a coating. That might be a different thing though. That thing will be like this, na? Remember the thin film experiment. So all that blue light and all will have a destructive interference for you. These are easy ones. We'll see them. You guys remember this? What does a white light do? If you shine a white light in a YDC experiment, you will not get any fringes. The pattern will look like this. You guys should definitely check out these cases. Huh? We did around some 10 cases here. Look at this one, 11A, B, position of blue and freeze. C, if you use light bulbs are incoherent. The whole thing will be eliminated. D case, alpha particles. E case, light rate and angle. F, the whole thing is filled with medium, fringes will shrink. G, if the slit width is different. This is a white light. This is how the pattern will look if you use white light. The central fringe will be white and the rest of the thing will get messed up. So this thing actually has a use. Central fringe is the only point where for all the wavelengths it is a central maxima. So white light is used to find the position of central maxima. Are you getting it? So that is a use of white light. So before doing a YDC experiment, people shine the white light. They'll get a white spot. So they mark that as x is equal to 0. And then they start the experiment with monochromatic wavelength. Then we had I case, missing wavelengths. Right? So there are multiple cases there. And then we did 3 experiments are there. One is the Lloyd's mirror. One is the Fresnel biprism experiment. Then Quincke's tube. Yeah? Quincke's tube is an experiment to find the speed of sound. So there are 3 experiments in this. So definitely check it out. Now get this thing. In Young's double slit experiment, the central branching can be identified by shining white light plus direct law. What about this thing? So intensity is proportional to area of the slit. So if you have more area, more light will pass. So you have more this thing. So the intensity will be I1 by I2 will be in the ratio of n by 1. Imax by I minimum, the formula will be root I1 plus root I2 whole square, root I1 minus root I2. This is the first question which we did in wave optics. The interference. Substitute there, you'll get the answer. Proper mains level questions. Clear with us? This is another good one. You have medium on the left side, 4 by 3, and the medium in the middle, 10 by 9. You have 2 different mediums. And the lighters are coming at an angle. Let's see. Hmm, it looks scary. It would have been scary if the point was this. All right. So let me take that point and let me show you for that. O you can do. O is not a big deal actually. So let's take some point here A, some point P here, and let this distance be some 3 mm. Okay, I'm doing for P. Now see what is happening. The light rays are coming from infinity, and after this, they're going to travel to P. Now the problem is the light rays which are coming from outside are traveling in 4 by 3. The light rays which are traveling here are traveling in 10 by 9. So it's messed up. So from this point, if you drop a perpendicular, so initially this was the extra path difference. So this is the path difference in the outside medium. Agreed? That means the light rays which are reaching S2, they have traveled an extra distance of delta x because of that angle. Now, same story again, you want to find the path difference at point P. Now, let's write that carefully. Can't split this anyway, so I think. So you drop a perpendicular here. This would be the extra path difference delta x. This is P. This should be a good advanced question though. And let's say this distance is some y. Okay, great. So listen carefully. You want to write the path difference for P. So the light rays which are reaching S2, they are traveling. Now again, the problem here is since they're traveling in two different mediums, we have to bring a common medium. So we will convert all the path differences into vacuum. So that is the first thing. If light rays is traveling through different mediums, you will get confused. So best thing, convert all into vacuum. Convert all path differences in terms of vacuum. And how do you do that? Simply multiply with mu, isn't it? If a light ray is traveling through a slab of mu, it behaves like it is traveling in vacuum of thickness mu d. Remember that? So convert all path differences into vacuum. Perfect. So when you're going to P, this delta x which I got, how much is that? This was d sine theta. But you're traveling in which medium? Mu1. So that will be mu1 into d sine theta. Then you started going from S2 to P, but in which medium? You're going in mu2. So mu2 into S2P. So this is one light ray which has gone down. So I'll do one thing. I'll mark this in green color. This is that green wala. Okay. Minus S1. Initially, there is no path difference. This thing traveled mu to S1P. This is this sky blue thing. I think that's called TL. Yeah, done. So what are the path difference there? So that will be mu1 d sine theta. This will be mu2 S2P minus S1P. I hope you remember what is that. S2P minus S1P is dy by capital D. But in our question, S2P minus S1P will be 0, na? Because O is the center. So it doesn't matter here. So that becomes easy there. So mu1 d sine theta plus mu2 dy by capital D. This is the path difference in vacuum. So if you want phase angle, then this should be 2 pi by lambda in vacuum. Make sure you're converting everything into vacuum. There, you'll get whatever you want. Clear with this? So in our question, he's talking about O. So S2P minus S1P ka term is 0. So this is gone. So the path difference is mu1 d sine theta. Now, actually, you don't even need mu1 there. No, you need that because anyway, lambda is also given in vacuum only. So you have to convert everything into vacuum. Clear with this? This would be a much better equation. And they really fired up and they want to mess it up, they'll put two slabs also. And if they're really gone crazy, then they'll put two slits here and they'll put one more screen here. Remember that double YDSA? That would be fun. We will see that later on anyways, but I think this much is sufficient. But is this clear what I did? That's a pretty good question. You should definitely check it out. Let's get this. The films of thickness is TA, TB, refractive index is mu A, mu B, central maxima will. Remember the formula? We just now derived this. This was the shift. So mu1, mu2, mu medium is 1. So he indirectly gave you outside is not given. So shift will be d by small d t1 mu1 minus 1 minus t2 mu2 minus 1. Clear with this? So t1 mu1, t2 mu2 will cancel. You will be stuck with d2 t2 minus t1. I hope that was right. So now see, if t2 is greater than t1, it is positive, means it will shift upwards. Right? A and B are two slits, so you will shift towards A. If t2 is less than t1, you will shift towards B. Clear? So this is TB and this is T. I think that is better to write. Shift towards A. Yeah, B is the answer. D is the answer. Okay? Yeah, B is the answer. What about the next one? So most people think it will not shift. Be careful. The formula is T into mu minus 1. Why is there mu D? Which case, right? This one.
Yeah, this I the mu1.
This one.
Yeah.
Because this outside medium is 4/3, na? Outside medium, it's not vacuum.
But they have not specified the thickness of that medium.
Come again.
Don't know the thickness of that medium, right? So if you're
Why
taking
do
it,
I
considering
care?
it as
We don't care, na? See, till here that this distances are equal, na? Problem ये problem है ना? That is a problem.
But why are we multiplying it by?
Because you're converting everything in vacuum. You're traveling in a medium. How can you compare when light ray goes from, let's say the light ray is going through two different mediums? Can you just subtract the regular distances and say path difference will be same? So you have to bring them to a common platform, right? It's like saying, let's say, I have 100 rupees, you have 100 euros. Can I say we have same amount of money? Because we both have 100 and 100. Getting it? Problem wo hai. Both are not same. Even though the numerical looks same, we are actually converting, we are two different currencies. You just can't add them up. So what we do, we bring them to a common platform. Maybe we convert both of them into dollars and then we'll compare. Something of that sort. So when a light ray goes from different mediums, you convert them into something common. You don't like vacuum, fair enough. You convert into one of the medium then. I like vacuum because it is easy enough if mu se multiply karna tha. That's the only thing. What about this guy, everyone? If you keep a slab of refractive index which can be varied in front of the slits, what will happen? So initially the intensity will be maximum. If you put a slit, what will happen? The fringe will shift. So as the fringe is shifting, what will happen? Bright fringe will become dark fringe. And if you still keep increasing, then the shift will continue to shift. Then first maximum will come there. Are you getting it? So intensity will decrease and then increase. Which option? See. Is that logic making sense? If you put a slab and if you keep on increasing mu, the shift will keep on happening. Shift means what? The central maxima, the pattern will keep moving, na? So central maximum will go up, let's say, right? The first minima will come towards the central minima, central maxima position. Then first maximum will come to the central maxima position. So the pattern is continuously moving. So intensity will actually continuously increase, decrease, increase, decrease. This will never stop. Are you clear with that? So we all agree, right? When you put a slab, pattern shifts. And if the pattern is continuously shifting, so the bright will become dark, dark will become bright. It's a easy, good question. Both are pretty good ones. These are really good mains level questions. Not too tough, but you need to think. There's nothing like you will just, mug up and give the answer there. This is still a good one. Let's see how will you handle this. Numbers are, this is A, this is the source, and this is B. So they have two mirrors. The angle theta is small. Find the fringe width. Just get me the main equations. And remember, in YDSC, somehow you have to create two sources. So there are two reflections. So how do we handle this? So basically, these are two mirrors. Let's take one of them, then automatically other will take care. This guy is theta. So this is the source. And where will the image be? Image will be exactly perpendicular to this. Somewhere here. If that is theta, this is 90. 90 minus theta, this is theta, this is A. Then this distance will be A cos theta. This also will be A cos theta. So from here, if you drop a perpendicular, that will be 2A cos theta, tan theta. And this distance will be 2A cos square theta. Similarly, that also. So now we actually have two sources, I1, I2. This was the source and this was the screen. This distance will be 2A cos square theta. This distance was B. So this is capital T basically. B plus 2A cos square theta. Theta is small, so you can actually make theta 0 there. And this distance between them will be 4A cos theta tan theta. This is your small d. Okay, so these two things are acting like slits and there. So fringe width will be lambda capital D by small d. Clear with this? Since theta is small, you can make cos theta 1 and tan theta theta. This is the catch. So you get two images, kind of like Fresnel vibrism experiment, but little different. We are using mirrors here. Easy? These are not tough, but if you have not seen for the first time, it looks a little weird, like, okay, what the hell is happening? So that is the main thing. And if you see it is the same thing repetition. If you see, we're always finding the path difference and we are trying to solve. We are doing nothing new as such. Let's get these two. Same equations, similar ones. Let's see. If the first minima in a YDSC occurs directly in front of the slit. So basically, yeah, then it's a straightforward question. No? So we got a slit, this was there. So rightly exactly in front of it. So basically this distance was d by 2. So path difference delta x is dx by capital D, and D is saying it is the first minimum, so this should be lambda by 2. And x is nothing but d by 2. So lambda is equal to d square by capital D. This is that missing wavelength wala. And interference is observed due to two coherent sources. So you can substitute the values and check. It didn't say which minima, right? So 2n plus 1 lambda by 2. D square by 3d, d square by 5d, and so on. So this is our missing wavelengths one. And interference is observed due to co-coherent sources A and B having phase constant 0 separated by 4 lambda along y-axis. Detector is moved on the x-axis. This is also the same story. So from here to here, the path difference delta x will be 4 lambda. When they go to infinity, path difference will tend to 0. So it means you have somewhere here 3 lambda, 2 lambda, 1 lambda, 3 lambda, 2 lambda, 1 lambda. Infinities are not counted. That will be, he's anyway asking from 0 to infinity. That's 4. Easy? Can't use a regular formula. We can't use the regular formula because capital D and small d are close by. वो भी सही है. I hope, let's see, वो भी है. I didn't see that numbers. Small d is how much? 5 centimeters. This is only 12 centimeters. This is not small. You're right. So when I go here, what is the path difference? So this guy will have a path difference of 12, and this guy will go 12 square plus 5 square, 13. This is wrong, everyone. I did wrong. Your D is comparable. That's what I was thinking, why it got repeated. D is comparable to small d. So you can't use that delta x is not equal to d sine theta. You literally have to solve. But I think numbers are good. S2 and this is S1. So delta x will be S2p minus S1p, that's 1 centimeter. This must be 2n plus 1 lambda by 2. Therefore, lambda is equal to 2 by 2n plus 1. There. Now you solve, you'll get the answers. You're right, Isha. That was a mistake. Be careful. What about these two? This is that Lloyd's mirror, if you remember. A long, narrow, horizontal slit, 1 mm above a plane mirror. The interference pattern produced by the slit and its image is viewed on the screen. 1 meter from the slit. So that's why they're in this distance. Distance of the first maxima above the mirror is equal to. So what is Lloyd's mirror? So when you keep the source here, the light ray will hit and bounce off to the point here. Let's say this is the screen. This is point P. So it feels as if the light rays are coming from this point I. So these two will act like sources. So initially, if this distance was, let's say 2 centimeter, and this also will be 2 centimeters. So this distance will be small d. Now, the only difference here is because you're hitting a mirror, this will get an extra path difference lambda by 2. So when you write the equation delta x, so it will be IP plus lambda by 2 because of reflection minus SP. And we know IP minus SP, that's again your regular formula, dx by capital D. D is the distance between the source and the image, capital D is the distance. What you want to find? First minima, first maxima, so this will be in lambda for maxima. You will get x value from there. Clear with this? That is the only thing. In Lloyd's mirror, the image which you create will not be in phase, it will be out of phase by 180 degrees. That means it will feel the light ray has traveled extra lambda by 2. That is the main thing there. This thing is actually from diffraction. Do you guys remember the result? Read the question. Direct question, this thing. This is the result you should definitely mug up. In diffraction, there are like 6 results you have to remember. This is one of them. So in a single slit experiment, the phase difference between the rays coming from the two edges of the slit diffraction में if you remember ये statement था याद 2 pi. Because if you remember how we did this derivation, again, not a full derivation, but when we take two points, we take two points, right? And we try to find a minima. For 2 points of a by 2, the phase difference is pi. For again 2 points, again it is pi. The total will become 2 pi. So that's a 2 pi ka result. Clear with this? That's one good result. Again, understand, like I said, you're not writing only mains, you're writing 2 mains, 2 bits. Now CET also became twice. UGE exam, Manipal, Vellore, right? Advanced. So in total, 10 exam ho gaya roughly. So questions will keep coming in some or the other. And don't think like, mains, I do understand there is a time crunch. You're trying to do a lot, but time kafi nahi hai. That is okay. All I'm asking is this. Let's say till mains 1, you give your best every day, do as much as you can. Let's say by mains 1, you can finish only 50% of portion thoroughly. I'm just saying you can do more, right? Now, there is nothing to feel bad about it. It's completely fine. Then you have February, boards is there. Boards ka max exam will happen by third week or fourth week. Uske baad 10 din ka break hai for computer science. So mostly by March first week, you are done. So by the time when you write the mains 2 exam, can't you take this 50% to 60-65%? Right? 65%. Then bits 1 will come in May first week. By then, can't you push it to 75%? Bits 2 will come in June ka last. By the time you reach bits 2, can't you reach this to 90%? Your preparation does not end in June. Getting it? Because some of you are getting overwhelmed. Sir, itna karna hai, itna karna. I understand, bahut karna hai. So whatever you can do thoroughly, na. There are 20 chapters to do, but you think you can do only 10 chapters properly. Let's finish all the 10 properly first. Right? Plan for the stuff and do it. All you need to do is crack one exam. Getting it? So mains 1 is our first target, but still. Okay, with that, we'll wrap up for the day. Next, when we catch up, we'll continue from here. We will start off wave optics also. But if you see wave optics at a mains level, there is really not much. Maybe advanced with a few more varieties we can mix up. But if you understood today's whatever I taught you, I think the major thing is this only. Now, again, if you see the schedule, Monday, we don't have a class, right? So our next class will be directly on Wednesday only. So this Monday, there is no class, but